Good morning. This is Hope Reactor. Now, let's begin today's news.
Mine video script. Japan found a smarter way to crack rock underground. What if the best way to crack solid rock underground was not to use more force? Deep beneath Japan, researchers are exploring a completely different approach. Instead of simply increasing pressure until the rock breaks, they are developing a special fluid that can first make the rock easier to fracture. It can stay where it is needed. It can chemically weaken the rock. And it may even help prevent the newly created underground pathways from becoming clogged. This technology is still at the experimental stage, but if it works at larger scales, it could help unlock one of Japan's most important domestic energy resources, geothermal power. So how does a liquid make solid rock easier to break? And why could this matter far beyond geothermal energy? Let's look underground. Japan sits on one of the most geologically active regions on Earth. That creates obvious risks, including earthquakes and volcanoes. But it also gives Japan something extremely valuable: heat. Huge amounts of heat exist beneath the ground. Geothermal power can use that heat to generate electricity without depending on sunlight, wind, or imported fossil fuels. Unlike solar power, geothermal energy can operate at night. Unlike wind power, it does not need the weather to cooperate. In theory, that makes geothermal energy especially attractive for a country like Japan. But there is a problem. Finding hot rock is not enough. To extract useful energy, water needs a pathway through the underground rock. It must travel through fractures, absorb heat, and eventually return toward the surface. If the rock does not contain enough connected fractures, engineers may need to create or expand them. One method is hydraulic fracturing. Fluid is injected underground under pressure. The pressure creates cracks in the rock, opening pathways through which water can circulate. But deep underground, conditions become extremely difficult. Temperatures rise, pressure increases, and ordinary water can become less viscous. In simple terms, it becomes easier for the water to escape into tiny, existing cracks and pores. That creates a frustrating problem. You want the fluid to stay near the place you are trying to fracture, but instead, some of it may leak away through the surrounding rock. So engineers could simply make the fluid thicker. That sounds easy, but there is another problem. A thicker fluid can require higher pumping pressure. Now we have a contradiction. You want a fluid thick enough that it does not escape, but you also want to avoid using unnecessarily high pressure. This is where the new idea becomes interesting. Researchers combine two different functions inside one fluid. The first comes from a compound called GLDA. GLDA can be produced from glutamic acid and is known as a biodegradable chelating agent. That sounds complicated, but its job is surprisingly simple. It interacts with minerals inside the rock. Instead of waiting for pressure alone to overcome the full strength of the rock, the chemical reaction can weaken parts of the rock first. Think of it this way. Imagine trying to break a thick piece of material. One option is to hit it harder and harder. Another option is to create a small weak point first. Once that weak point exists, much less force may be needed to start the fracture. That is the basic shift. Not simply use more pressure, but change the rock before you break it. And GLDA has another useful property. When minerals dissolve, metal ions can be released into the fluid. Those materials can sometimes react again and form deposits that block underground pathways. Because GLDA can bind to some of these metal ions, it may help reduce this secondary precipitation and clogging. But chemical weakening alone is not enough. The fluid also has to stay where it is needed. For that, researchers use another substance called scleroglucan. Scleroglucan is a polysaccharide produced by microorganisms. Its purpose is to give the fluid viscosity. But the most interesting part is how that viscosity behaves. The fluid does not behave exactly the same everywhere. When it moves quickly through larger pathways, its viscosity can decrease, allowing it to flow more easily. But inside smaller pores or slow-moving regions, it can remain more viscous. That means the fluid may become easier to pump when it needs to move, while still resisting escape into places where researchers do not want to lose it. It is almost as if the fluid changes its behavior, depending on the underground environment. Move when necessary, stay when necessary, and react with the rock when it arrives. Researchers tested this concept using volcanic rock. They compared ordinary water, a thickened fluid without the reactive chemical function, and the new reactive viscous fluid. The results suggested something important. By combining chemical weakening with controlled viscosity, the researchers were able to promote fracture, formation and fracture opening, without causing the required fracturing pressure to rise excessively. That is the real breakthrough in the idea. For decades, fluid in underground engineering has mainly been treated as a tool for transferring pressure. Pump it down, build pressure, break the rock. But this new approach gives the fluid a much more active role. The fluid itself can participate in deciding how the rock breaks. It does not simply carry force, it changes the underground environment. And that could become especially important after a fracture forms. A newly created crack is useful only if it stays open. If the surrounding rock closes again, the pathway can disappear. Traditional underground engineering sometimes uses solid particles, called proppants, to help hold fractures open, but chemical reactions could potentially make the rock surfaces rougher. A rougher fracture surface may prevent the two sides from fitting perfectly back together. Researchers believe this could eventually reduce dependence on conventional proppants in some applications. But there is an important reality check. This does not mean geothermal drilling has suddenly become easy. The experiments were performed under controlled laboratory conditions. Real underground environments are far more complicated. Temperatures can be much higher. Stress inside the rock can be enormous. Different rock formations contain completely different minerals. Groundwater chemistry also varies from place to place. So the next question is not whether this fluid works in a laboratory. The real question is whether it can continue to work. Hundreds or thousands of meters underground, researchers will need to test different temperatures, pressures, rock types, chemical concentrations, and operating conditions. There are also economic questions. The fluid must not only work, it must be affordable enough to use at industrial scale. But the potential applications are much larger than one experiment. If engineers can create underground pathways using lower or more controlled pressure, this concept could support geothermal energy development. It could also have applications in underground carbon dioxide storage, natural gas extraction, underground hydrogen storage, and other technologies that depend on controlling fluid movement through deep rock. For Japan, geothermal energy is particularly interesting. Japan imports a large share of the energy resources it uses, but geothermal heat is already beneath Japanese soil. The challenge is not simply discovering that heat. The challenge is accessing it safely and economically. And sometimes, the technology that changes an entire energy system does not look dramatic. It may not be a giant power station. It may not be a futuristic reactor. It may simply be a carefully designed fluid, disappearing into a hole in the ground. A fluid that knows how to flow, a fluid that knows how to stay, and a fluid that makes rock easier to fracture before brute force becomes necessary. Instead of asking, how much harder can we push? Researchers are asking, how can we make the underground environment easier to work with? That is a very different philosophy. Not stronger, smarter. And if technologies like this continue to develop, Japan may be able to turn more of the heat beneath its feet into reliable domestic energy. Sometimes the next energy revolution begins in a place we cannot even see, deep underground, inside a tiny fracture in a piece of rock. Something unknown today may become a source of hope tomorrow. This is Hope Reactor.